So as I said, when I met you yesterday morning, we're continuing to spend some time here in Chapter 5, still continuing to study the Euler Totient function and learn about it and see applications of, well, we're particularly interested in showing applications of the multiplicative formula for the Euler Totient function. This is very useful to have if it focuses. So we've got a nice formula through which we can understand the values of the Euler Totient function in terms of the prime factorization of the argument n. So if we think of n as a product of these powers of primes, this is what the value phi of n looks like, a very related product. In the course of proving this, we established that phi was multiplicative. So if you evaluate it on a product A and B, which are co-prime, the value is equal to phi of A times phi of B. So very much we're applying those two properties along with things we already know, such as the fundamental theorem of arithmetic. Okay, so we're seeing lots of applications of these results and learning more about phi at the same time. So yesterday morning, we spent the whole time studying this question, finding all the values n for which phi of n is equal to 12. So all those integers for the multiplicative group of congruence classes modulo n had size 12. So today I'm going to begin with looking at this question, and there's a slightly related question in the problems we can have a look at as well. So this is an example 5.1. Some other properties of phi. So this is number 1. So that phi of n equals phi of 2n if and only if n is odd. Okay. Well, so this is quite an interesting result. Whenever you've got, say, the multiplicative group of congruence classes modulo whatever, modulo 25. 25 is an odd number. This is telling us straight away that the multiplicative group of congruence classes modulo 50, which is 2 times 25, that will have the same size. Okay. So we'll look for a proof of this. So i.e., the size of the multiplicative group of congruence classes modulo n is the same as the size of the congruence classes modulo 2n, if and only if n is an odd number. Okay, so it's an equivalence. It's an if and only if. So the most conservative way, most patient way to approach this is to prove the two directions of it. Okay. 5.1, part 1. This is page 36. Page 36. So, well, one way, I mean, if we assume n is odd, then you see we can deal with this one quite quickly, because if n is odd, what is phi of 2n? Or how should we think of it? Well, the definition of odd is you're not divisible by 2. So if you're not divisible by 2, your greatest common divisor between yourself and 2 is what? Okay. So another way of saying n is odd is saying that the GCD of 2 and n is 1. Because 2 only has 2 divisors, namely 1 and 2. So if the greatest common divisor is 1, then it means n is not divisible by 2. Okay? But when you look at it that way, it immediately makes you think of the multiplicative property of the phi function. Okay? Remember, a function in number theory, it's called multiplicative if, whenever you evaluate it on a product, if the factors in the product are co-prime, then you can break this single value of phi down as the product of the individual values. So we can say this is equal to phi of 2 multiplied by phi of n, since phi is multiplicative. remember the multiplicative property is GCD of AB equals 1 implies 5AB is 5A times 5B. So we're applying that in the case of 2 and n. What is 5, 2? 5n we don't know, but 5, 2 we do. It's just 1. Yeah. So there's how many integers between 1 and 2 are co-prime to 2? Well, there's only 1. So this is equal to 5n. That's 5, 2 as well. So that direction is rather quick. What directions are they? So what about the other direction? So for the other direction, which is i.e. 5n equals 5 2n, but this implies that n is odd,
why n is odd?
well, no, I'm just saying that's the other direction. I'm not claiming I've proved that yet. I'm just this is the other direction. This is what we now want to prove. Okay, so well, we're kind of a little bit. This direction, as it's currently phrased, is a little bit awkward. Okay, because what I'd maybe like to do is, okay, assume that 5n is equal to 5 2n. And I'm probably going to want to use the multiplicative formula. But if you think about the multiplicative formula, I want to imagine what the prime factorization of n is, and then I can represent 5n. And then I'll also imagine what the prime factorization of 2n is. Of course, the prime factorization of 2n is the same as this, but just with an extra factor of 2 in front of it. Yeah. Because prime factorizations are unique, so you get the factorization of 2n by just taking twice the factorization of n. But the difficulty is I don't know how to represent the prime factorization of 2n, because I don't know if there are any 2's already in n. I mean, it all comes down to the action and the influence of the 2. But I can't assume that there are 2's in n or there aren't, because like I'm trying to prove that n is odd, but there are no 2's in n. So the setup is a little bit frustrating for proving it in this direction. So as we've seen in other examples, when we've been trying to prove an implication and it just seems a little bit awkward or set up in not a nice way to get a hold of, one technique that we've used before is to instead try and prove the contrapositive, okay, which is an equivalent formulation of this, but is the implication in the other direction amongst the negations of those two statements. Okay. So it seems hard to get a hold of this. So we'll try instead to prove the contrapositive. And i.e. the contrapositive says if n is not odd, so in other words n is even, that implies not that these two are the same. So 5n is not equal to 5 2n. Now this is easier to get a hold of because we start off with the assumption that n is even. So the first thing to recognize is this is the contrapositive. This is logically equivalent to the previous statement. Okay? Previous statement says if the phi values are the same, n is odd. We're going to prove instead if n is even, that forces the phi values to be unequal. Right? So that means if they are equal, n has to be odd. The statement and its contrapositive are logically equivalent. So we assume n is even, and that gets us started a lot easier. Okay? Because if we assume n is even, that tells us immediately what to do. Just automatically. If someone tells you n is even, what should you immediately do? In number theory. Sorry? Sorry, just thinking. I mean, see, we're always looking for ways to move forward, for ways to, work with what we're given. We've got this n. We're trying to prove that these two phi values are not the same. But somebody's just told us that n is even. We've just assumed for ourselves that n is even. Okay, so we're trying to prove this implication. So we assume the bit on the left. We're trying to deduce the bit on the right. But what's just a natural instinct, just without thinking? Take the factor of 2 out of it, and what's left behind? I mean, we can always take a factor of 2 out of any number. It might leave a number of halves behind when you take it out. But we're told n is even. So we take the 2 out, what we know is that there's an integer left behind. 2 divides it. So, i.e., n is equal to 2 times m for some integer m. That's the point. I mean, you can't do that with every integer n. You can't just assume you can take a 2 out of an integer and leave an integer behind, because it might be odd. But we're told n is even, so we should emphasize that fact, okay? But now, what's this m that's left behind? Or if you're taking factors of 2 out, you may as well go the whole hog, right? And take all the 2's out. And this is with the view to, again, using the multiplicative formula later on, because n could still be even. So I'm not yet looking at a product of co-prime factors necessarily. So what I'll do is I'll just ensure that I've taken all the factors of 2 out. So keep going. I can take maybe some number of 2's out, okay, for some integer k greater than or equal to 1, because I know n is even, so there's at least one factor of 2 in there. Actually, I won't call it m, because I just called that, so s, let's call it s. And what do I know about this s? If I've taken all the 2's out of n, what property does the s have? If you take all the factors of 2 that there are within n, you suck them all out, what's left behind? An odd number. Didn't see who said that, but it's correct. But s is odd. Okay. So an even number, yeah, it's divisible by 2, but it might be divisible by 4 or 8 or 16 or 32 or 64, 28, etc. So take all the 2's out of them, and what's left behind is odd. And now we're looking at a product of co-prime numbers. 2 to the k and s. The GCD of 2 to the k and s is 1. So that tells me that if I want to look at phi of n, that's to look at phi of 2k times s. If I can use the multiplicative property to say that's phi of 2k times phi of s. So that's using the multiplicative nature of phi. Yeah? Now, which of these can I develop further? Well, which of them? not 5s, because I don't know what s is, but 2 to the k I can develop. So what is 5 2 to the k? Just apply the multiplicative formula, right? So that's a prime factorization of this number. It's 2 to the power k. So the rule is you reduce the power by 1, so 2 to the k minus 1, and you multiply by 1 less than the prime. But this is the factor 2, so 1 less than it is just an extra factor of 1. So I won't bother writing that down. Yeah. So 5 2 to the k is 2 to the k minus 1, and this still multiplies the 5s. Okay. Well, that's 5n. Remember, I'm trying to prove that 5n is not the same as 5 2n. So now let's examine 5 2n. And I might discover they're the same, in which case the thing is wrong, but let's think about what 5 2n is going to be. Well, n we're representing as 2 to the ks, so the natural way to represent 2 times n is 2 to the k plus 1 s. Yeah. Yeah. S is odd, so these two numbers are again co-prime. So the first one only has factors, powers of 2, but the other one is odd, so it doesn't have any 2's in it. So they're co-prime. So I can say this is phi of 2 to the k plus 1 times 5s. And again, okay, I can't do anything with 5s. We don't know what s is, but we can do something with 5 2 to the k plus 1. It's 2 to the k. Again, just applying the multiplicative formula. So we're comparing 5n with 5 2n. We're comparing this with this. What can we say then? These two quantities here. Do they look the same? No, they don't. Can we say for definite absolutely that they're not the same? Okay, they look different. 2 to the k minus 1 times 5s, 2 to the k 5s. They certainly look different, but there's one special case which they maybe might be the same. How could these two quantities actually be the same? Well, if 5s somehow managed to be 0, then they'd both be 0. But of course, 5s can't be 0. Because s is an odd number, an odd positive number. So 5s is going to be at least 1. Okay? Because 1 is always co-prime to s. Remember, 5s is the count of the number of integers less than s that are co-prime to s. So it's at least 1. Okay. So this is certainly not equal to 2 to the k minus 1 5s, as 5s is bigger than or equal to 1, and this is equal to 5n. So 5 2n is not the same as 5n. That's required. So that proves the contrapositive, okay? Because we assumed n was even, and now we've reached the conclusion that 5 2n is not the same as 5n.
From where I.
Yeah, so you see, this was I'm trying to prove that implication. So I need to examine these two values and show they're not the same. Well, 5 2 times n, well, I've just established this way of representing n. So 2 times n is just going to be one more factor of 2. 2 to the k plus 1 times s. So I multiply that by 2. So it raises the exponent by 1. 2 to the k plus 1 and s are co-prime because s is odd. S was odd, so for the same reason as up here, the GCD of 2 to the k plus 1 and S is also 1. Okay. So because the Euler Totient function is multiplicative, you can split up this value as product of the two values. And this value you can write down straight away using the multiplicative formula, because it's a single prime to some power. So the phi value is the same, the power of the same prime, but one value less in the exponent. So it was k plus 1, so it reduces to k.
One.
I'm applying the multiplicative formula here.
Oh, okay.
Yeah, because when you have n as pi to the ai, you reduce the power by 1. And you also get that extra factor, pi minus 1. But in this case, the prime is 2. So the extra factor is just 2 minus 1, 1. So I don't bother putting it down. So it's just 2 to the k phi of s. And then I can compare that back to what I got for phi of n. And they're clearly different, because phi of s is at least 1, so it's not 0. 0 would be the only case where these two expressions actually are the same quantities. They're both 0. So that means I've proved the contrapositive, that n even implies these are different. So that means if they're the same, n has to be odd. And that completes the proof. Okay. So we know that for odd numbers n, these two groups have the same size. Okay. It's the same number of numbers that are co-prime to the modulus in both these cases. Okay. Now there's a kind of a related question. It's on a similar theme. In fact, I wonder, is it even... No, sorry. Okay. So exercise 5.1, question 3. So phi of n equals n over 2 if and only if n has this very special form that it's a power of 2 for some k greater than or equal to 1. Well, one direction of that comes out straight away from applying the multiplicative formula. Okay? Because if n is a power of 2, then phi of n, just applying the multiplicative formula, is 2 to the k minus 1, which is exactly 2 to the k divided by 2. Okay? So the direction from right to left of that comes out immediately just from the multiplicative formula. Okay. The other direction is well, again, we're going to do it by proving the contrapositive again. That's what the hint in the question is basically saying. For the other direction, again, we'll tackle the contrapositive. Contrapositive is a very useful technique when you're going to do here, because so the other direction we have to prove is that if the left is true, then the right is true. Okay. So we'll try the contrapositive of So this is what we're trying to prove at this point, that 5n is n over 2, that implies n is a power of 2. We're going to do the contrapositive of that. So we assume n is not a power of 2. And now we're going to prove that 5n is not n over 2. Yeah. So if n is not a power of 2, what does that mean? That implies we can represent n, and this is the guidance you're given in the question. We can represent n as 2 to the r times an m. Now, you can always represent any number like that. You can always potentially take out the 2's out of any number, although you have to allow for the fact that there are no 2's in it. But if we're assuming n is not a power of 2, then that means we're assuming m is not equal to 1. So that m is an odd number strictly greater than 1. So where m is odd and m is greater than or equal to 3. Okay, because if m was 1, then n would be a power of 2. But we've just assumed it's not a power of 2. So let's go. Let's have a look at 5n. It's phi of 2 to the r times m. So these are co-prime. GCD of 2 to the r and m is 1, okay, because m is odd. So I can write this as phi of 2 to the r times phi of m. I'm trying to prove here that 5n is not n over 2. Brain. All of the hints for you. To do this right in the form, choose and write index of the 2 lines. And so I think I'm going to abandon my attempt to prove it using the contrapositive, because I've just reread the hint there. I should obey it. So this is an example. This is instructive where, I set out to try and use the contrapositive, but it looks like the contrapositive is the awkward one here. Not sure how to proceed. So sorry, go back again. Yeah. So start again. Start again for this other direction. So if there are any 2's in n, we suck them out into this factor 2 to the r. And the only thing we assume then where m is odd. Okay, so we take all the factors of 2 out of n, package them up as 2 to the r, and the bit that's left behind, m is odd. Now that looks like what I just did, but here it's left open the possibility that m is 1, which is what we really want, okay? Because we're trying to prove the other direction, that the left implies the right, because we've done the right implies the left. So now we're trying to do the left implies the right, okay? So we assume that phi of n is equal to n over 2. Yeah, this gets it for us, I believe. But applying the multiplicative formula, says that phi of n is phi of this 2 to the r m by the multiplicative property. This is phi of 2 to the r phi of m. But if I'm assuming that this is n over 2, i.e. this is, see, n I'm representing like this is 2 to the r minus 1 times n. But this, if I apply the multiplicative formula to that bit, that gives me 2 to the r minus 1 times phi of m, which is supposed to be equal to 2 to the r minus 1 times n. Okay? But that implies that phi of m is equal to n. I can cancel the 2's from both sides. Now, which numbers satisfy that? But remember, phi by definition is the number of i's in the range between 1 and m, such that the GCD of I with m is 1. Okay, the number of numbers in the range 1 to m, such that GCD of I with m is 1. Now, if m is strictly bigger than 1, then the GCD of m with m is m, which is not 1. So that means phi of m, the most it can be is m minus 1. Because for all numbers bigger than 1, this last number, m itself, is not co-prime to itself. Okay? Because it shares the factor, the GCD of m with m is m. And if so, the greatest common divisor of 5 with 5 is 5. So that's not 1. 5 is not co-prime to 5. So it won't get counted. So that means that reduces the maximum number of these possible i's to, at most, n minus 1. And what are the numbers that achieve this maximum? Top question. So which are the special numbers that achieve this maximum possible value of 5m? If someone asks you what are the special numbers in number theory, there's only one answer to that question. The primes. Yeah. So the prime numbers are the only numbers that achieve this maximum. 5p is p minus 1. Because everything strictly less than p is going to be co-prime to p. because P doesn't have any other factors apart from itself and 1. So if n is strictly bigger than 1, the most that 5n can be is n minus 1. So the only time this can happen, that 5n is equal to n, is for that special uninteresting case of the number 1. The number 1, so n equals 1, and how many numbers between 1 and 1 are co-prime to 1 is just 1, namely 1. Nothing much going on there. Okay? So 5n being equal to m, this implies that m is 1. Okay, m is 1. What was m? Remember, m was the rest of the stuff in n apart from the 2's. So if m is equal to 1, it means all there is in n is really a load of 2's. So n is a power of 2. Okay, because this complementary factor isn't really there. It's just the number 1. So the prime factorization of n is just a bunch of 2's. So i.e., n equals 2 to the r, a power of 2. So that proves the second half of the implication, that 5n is n over 2 implies that n is a power of 2. So we know a few, and n is 2 to the r. Okay. So again, we're just building up different things, different knowledge about the Euler quotient function. Okay. Any questions? I think we've done almost all those exercises then from chapter 5. Next week we're going to do some, as well as answering questions about the coursework, which hopefully you've all looked at because the mathematics won't be done. Next week.
Oh, we have a lot of them.
Well, yeah, but so next week will be your last opportunity to ask any questions before the Christmas break. So we can do that on Tuesday. Well, I've also got some interesting stuff to look at involving primes on that day as well. So maybe we could, in the few minutes remaining, we could maybe look at some past exam papers, maybe. We don't have much time, just 10 minutes left this evening. But maybe we could just quickly look at previous exam to see what kind of stuff I've asked about. I think we've covered probably at least 2 questions worth of material in terms of, if you look at the past exams. Back to 2016. Well, since we've just been talking about the Euler 5 function, we could look at this question 2. I can do the third part, because that's relevant to one of the coursework things. So the first question is basically, it asks you to define the congruence relation. What's the definition of A being congruent to B? And asks you how does it relate to the process of integer division by n?
Which question are you looking at?
Question 2. Part B is a proof question. This was one of the parts of establishing the multiplicative formula, namely that phi of a power of a prime was p to the n minus 1 times p minus 1. He did that using a counting argument. But maybe I'll do part C. Part C is relevant for the coursework. I mean, we've done some questions like this before, but we can do another one here to remind us of the importance of the Euler Totient function. Okay. What's the remainder when we divide 2017 to the 9th to the power of 1975 by 40? So divide 2017 to the 1975 by 40. What's the remainder? So this question is asking that 2017 to the 1975 is congruent to what modulo 40 for which standard remainder? So between 0 and 39. Okay, the small positive remainder that is left after you divide something by 40. So we want to use properties of congruences. The first thing we can do is, okay, so this is a large number, it's hard to deal with. The first thing we can do is simplify the base. So the question is, what is 2017 congruent to modulo 40? So let's divide 2017 by 40 into 201. It goes 5 times remainder 1. And into 17, it goes 0 times. So it goes 0 times remainder 17. Yeah, 50 times remainder 17. So 2017. So this implies, so it's congruent to 40 to the 1975. So if I'm trying to find this R, I can instead deal with 40. Sorry, 17. What am I talking about? 17. This remainder. 17 to the 1975 is congruent to R mod 40. Okay, because 2017 is congruent to 17 mod 40. Okay, but this is still too large to deal with, 17 to the power of nearly 2000. So we want to reduce the exponent, and we can reduce the exponent with the aid of Euler's theorem. So by Euler's theorem, 17 to the power of phi of 40 is congruent to 1 modulo 40. So phi of 40 is a multiple of the cycle length of 17 modulo 40. What is phi of 40? Well, phi of 40 is 8 by 5, so it's 2 to the 3 times 5 is the prime factorization of 40. Once you know the prime factorization, you know the phi value. You reduce the power on 2 by 1. You multiply by 2 minus 1. That's just multiplying by 1, so I won't bother doing it. You reduce the power of 5 by 1, but that gives you 5 to the 0, which is again just 1. And you have an extra factor of 1 less than 5. So an extra factor of 4. It's 4 by 4, so it's 16. So every time I raise 17 to the power 16, I'm back to 1. So I should divide this exponent. Really, all I need to know is what this exponent is modulo 16. Okay. So 1975 is congruent to what modulo 16? So what's the remainder? Divide 1975 by 16. Goes in once, remainder 3. 16 into 37 goes twice, remainder 5. 16 into 55 goes 3 times as 48, remainder 8. 7. 48 plus 7 is 55. Yeah, remainder 7. So it's remainder 7. 1975 is congruent to 7 modulo 16. That's the remainder you get after you divide by 16. So my 17 to the 1975 is congruent to 17 to some multiple of 16 plus a remainder of 7. That's what I just found out here, 123. I'm not so interested in the 123. So this Q is 123 on 16. But using rules of indices, this is 17 to the 16 to the power Q by 17 to the power 7. This bit, Euler's theorem, tells me this is 1. So that's just congruent to 17 to the power 7 modulo. Sorry, we're back. Whoa. This is back to modulo 40. Yeah. So that's true because 17 to the 16 is congruent to 1 mod 40. That's what Euler's theorem tells me. So at the beginning, I was faced with 2017 to the 1975 divided by 40. Now I've reduced it to 17 to the power 7. Okay. Still big-ish, but doable. A lot more doable than the original problem. Okay. And at this stage, I guess you just have to resort to calculation. Okay. There's no other theoretical simplification we could do at this stage. So we'd have to start building up. We'd have to work out what 17 squared was. It's 170 and 17, 49, 170 and 119, 289? 289? Well, what is that congruent to mod 40? 9? 7 times 40 is 180, so that's congruent to 9 mod 40. Well, then we can very quickly go to 17 to the power 4. Congruent to 81 mod 40, which is congruent to 1 mod 40. So 17 to the power 4 is congruent to 1. So that implies 17 to the power 7, which is congruent to 17 to the power 4 by 17 cubed. 40, this is just congruent to 17 cubed. Yeah? Because the 17 to the power 4 is 1. Well, that's just congruent to 17 squared by 17. 17 squared, I already know, is 9. So 9 by 17 mod 40. So what's that? 90 and 63. 153. Which is whatever it is. 33. 3 times 40 is 120. Remainder 33. So 33. That's what the remainder is. Okay. So this ginormous number, which we don't have to access, don't have to calculate, but we do know that if you divided it by 40, the remainder you get is 33. And we're able to do that all just by pencil and paper, yeah, and using the theory of the congruences. Okay. So that helps you out with one of the coursework questions, but then the other one is about towers of powers. So you got to extend these principles to iterative powers. Okay, we'll end it there for this evening.